to begin your session, I request Dr. Ila to introduce you. Dr. Ila is here.
Yeah.
Sir, just give us 2-3 minutes. Just.
Okay. इसमें वीडियो कैसे ऑफ करें? ऑफ करना है।
Dr. Ila,
hello.
Yes, Dr. Ila, I request you to introduce Dr. Anil Kumar, sir.
Yes, sir. Good evening, sir. Welcome, sir. Good evening, Anil, sir. Are you there?
Yes, good evening, Ila.
Good evening, sir. So this is hello, everyone. This is a very good opportunity for me to introduce my supervisor here, Dr. Anil Kumar, sir. He is from PDBM Triple ITDM Jabalpur. He is associate professor in the department of the ECE, and he is research interest in multi-rate signal processing, filter bank design, and medical signal processing, image compression, and there are so many vast applications of signal processing in a different domain of engineering. So at this note, sir, over to you. Please start your presentation.
Welcome, sir, and we request you to start the session, sir. Sir, your voice is muted. Anil, sir.
Yeah. Thank you, and thank you, Dr. Nanda and Dr. Ila also. And today I am going to deliver my lecture, Application of Linear Optimization in Multi-Rate Signal Processing. Okay. So I am Dr. Anil Kumar, Associate Professor from IIIT Jabalpur, and mainly I am working in signal processing application. Following students are presently working with me in different domain, and these are alumni from my lab, and my area of research is multi-rate signal processing and application of optimization in signal processing application. So today lecture I am going to cover following things. One is introduction to multi-rate signal processing. Then we will discuss in multi-rate signal processing some basic concept are there, and then downsampling, upsampling, and different types of filter is there. Then we are going to discuss how we can design. In case of, if you see in lectures, you will see that the problem of design of filter is nothing but reduced to design of some optimization problem. For solving that optimization problem, we can use constraint optimization, linear optimization, or gradient based optimization, swarm based optimization. So for solving here, we are going to discuss the linear optimization, how we can use linear optimization for solving the multi-rate signal processing problem for designing of the different filter, two channel filter bank, M channel filter bank, and non-uniform filter bank also. So before moving to application of linear optimization, we will discuss what is multi-rate signal processing, why if digital signal processing is there, so why people are moving to multi-rate signal processing. Okay, so first thing, in digital signal processing, if you see, we are processing signal at single rate. Okay, at sampling rate at input, output, and within the internal node, sampling frequency is same. The sampling frequency is same. And in multi-rate signal processing, we can define DSP system with unequal sampling rate. For example, if you see wavelet transform, then in wavelet transform, your sampling frequency is something different. So what is motivation to this multi-rate signal processing? If this thing is there, so there are many applications where we have to process our signal at different sampling rate. Okay, so means we require sampling rate conversion. For example, if you consider speech signal or audio signal, in early stage of research, we are transmitting only speech signal. So in this case, the need of multi-rate signal processing is introduced for speech processing. So in this case, for example, speech signal, if we consider speech signal, then bandwidth of speech signal is 4 kHz. Bandwidth of speech signal is 4 kHz. So ideally sampling frequency, if you consider the Nyquist criteria, then sampling frequency is 8 kHz. And if you consider the audio signal, in that case, range of frequency is 20 to 20 kHz. So in this case, sampling frequency required 40 kHz. But if you consider different application, for example, if audio signal is there, in that case, if you want to broadcast that audio signal, in that case sampling frequency required, that is 32 kHz. And if broadcasted signal is there, if you want to store that signal, in that case sampling frequency required, that is 41 kHz. And if you want to store that signal on digital audio, in that case sampling frequency required, that is 48 kHz. So one signal is there, ideally sampling frequency required 40 kHz, but for different application, we require different sampling rate. So that sampling rate conversion, that is possible in analog domain. If you do in analog domain, so whatever your discrete time signal is there, that you have to convert into again into continuous time signal. And whatever your requirement is there, you have to resample. Okay, so in this case, analog to digital converter and digital to analog conversion is required. So this process introduced several noise. Okay, so to sort out this problem, the concept of multi-rate signal processing is introduced. And there is another way is that due to multi-rate signal processing, if you want to process selective, for example, spectrum of the signal is varying from 0 to pi, and if you want to process your signal 0 to pi by 2, so in that case, you can divide your signal into number of band and you can process your band independently. You can process your signal independently. Okay, so in this case, independent processing is there. In that case also, you require multi-rate signal processing. And for hardware requirement also, if you want to implement digital signal processing, in that case also, if you want to further reduce computational complexity as well as hardware requirement is there, in that case also you have to do multi-rate signal processing. These are some basic application. You can use multi-rate signal processing for audio processing, analog to digital converter, in a smart antenna, in communication system also, in cognitive radio, and in image processing also. So originally, as we have discussed, that concept of subband coding was multi-rate signal processing, or subband coding was introduced in 1976 as means to reduce the effect of quantization noise in speech coding. It is your multi-rate signal processing, or subband coding is nothing but frequency domain coding. It will divide your input signal into number of bands so that each band can be independently processed, and then we are downsampling each subband, and then depending upon your application, we are using processing unit, and at receiver side again we are upsampling and then synthesizing, and then we are getting your output. So in this case, for example, if you want to process your signal as a full band, in that case you have to process number of data size is more. But if you want to, we know that in higher frequency range your information is less, and in lower frequency range information is high, so we can divide your signal into bands, so we can consider each band independently. Okay, so this is basic block. In this case we are analyzing your signal with the help of this set of filters. So this structure at input side, we are saying that these are known as analysis filter, and at the receiver side again we are synthesizing your with the help of this set of filters. So this is known as synthesis filter bank. So this is basic block diagram. Okay, so if you consider advantage why people are going for subband coding, so as we have already discussed that the concept of subband coding was introduced to means to reduce the effect of quantization noise. For example, if we consider this signal, okay, in this case spectrum of the signal is this one. In this case, if we divide our signal into 3 band, then whatever the quantization noise generated in this band, in first band and second band, it will be not separated. There is no spreading of quantization noise from one band to another band. It means quantization noise localized to one particular band. Okay, and in this case energy of the signal is less. In third band energy of the signal is less, and in this case, for example, in first band energy in this case quantization noise is more. So subband coding, it will also prevent the masking of peak energy signal. Okay, and in this case for quantization, because each band is independent, we can use different step size. Okay, and in this case we can also do bit if for encoding purpose in digital transmission. For encoding purpose we can use bit allocation based on energy contents. For example, in this case energy is more, so you can use large number of bits for encoding your first bit, and if your energy in third band is less, so you can use less bit for encoding this signal. Okay, so ideally if you consider this system, if this system in an ideal condition, if you drive the transfer function of this system, it should be pair delay system. Transfer function means y of z divided by x of z. So in this case it should be a pair delay system. Okay, so in ideal condition, but in this case we are performing downsampling operation as well as upsampling operation. Due to some downsampling operation means we are reducing the sampling rate beyond the Nyquist criteria. Okay, so if Nyquist criteria is not followed, so in that case there will be aliasing distortion. Okay, and in this case your composing filter is LTI system. These are not ideal ones, so in this case it will introduce because this LTI system means they are acting in frequency domain. So they, because of this, in this case there will be the phase distortion, there will be amplitude distortion. So in subband coding system there are 3 type of distortion is there. So to reduce this amplitude aliasing distortion in subband coding system or in multi-rate signal processing, we are the concept of quadrature mirror filter is introduced. Okay, so these are the basic structure. These are the types of subband coding system in early stage of research. The concept was proposed for subband coding. In that case, these 2 type of structure have been proposed. First one is filter bank structure. In this case, this is used for subband coding application. And in this case, this structure, whatever your trans multiplexer structure is there, this is used for communication purpose. Okay, so if you see if you carefully absorb this structure and this structure, in this case you will see that there is LTI system is there, and downsampling operation is there, and upsampling operation. So we can say that in multi-rate signal processing is nothing but your multi-rate system is nothing but your linear time invariant system and subsampling operation, maybe downsampling operation or maybe upsampling operation. So moving further, we are going to discuss what is down two operation as we have discussed, that is decimation operation. Decimation operation is nothing but it is process of reducing the sampling rate, and it will take place in two steps. First we are performing filtering operation, and then we are performing downsampling operation. Or if you see the block diagram for downsampling operation is this, mathematically it is y of n equal to x of mn. Okay, and physical in this case sampling frequency is fs, then in this case sampling frequency is reduced by a factor of m. So in this case, if you see in time domain, for example, this is your input signal, it will retain every ms sample of your input sequence. So in this case data size is reduced. Okay, and if you see frequency domain, same thing in frequency if you see, so in this case in frequency domain, if you see downsampling operation in time domain, your signal is compressed. So in frequency domain your signal is expanded. Okay, so if you see this expression, if you convert this expression into z domain, then y of z equal to 1 by m. K is varying from 0 to m minus 1, x of z raised to power 1 by m, w raised to power km. So in this case, if you convert this thing in frequency domain, you will feel that the spectrum is expanded. Okay, spectrum is expanded, and in this case additional term is introduced. Means if you see in frequency domain, this is 1 by 2 x of e raised to power j omega by 2 and plus x of minus e raised to power j omega by 2. Okay, so in this case, this second term, if you see the effect of second term, that is nothing but same spectrum is shifted by 2 pi. So in this case, there is aliasing distortion is there. So to limit this aliasing distortion, there is filter. That filter is there, that is anti-aliasing filter. Okay, and similarly, if you see your interpolation operation is nothing but process of increasing sampling rate, and it will take place in two steps. First we are performing upsampling, and then we are filtering by low pass filter. So in this case, for example, this is your sequence. In this case, in time domain, your downsampling upsampling operation is nothing but y of n equal to x of n by l. Okay, so in this physical interpretation means in this case l minus 1 consecutive 0 is introduced. For example, l equal to 2. So in this case 1 0 is introduced between the samples. Okay, and this is in time domain. So same thing if you see in frequency domain. In frequency domain, your whatever your spectrum of original spectrum is introduced in between baseband signal L minus 1, baseband spectrum of your signal is introduced. So to eliminate that baseband spectrum, whatever your imaging effect is there, this filter is there. That filter is nothing but anti-imaging filter. Okay, so if you consider basic structure of channel, this is basic structure of your filter bank structure. In this case, we are dividing our signal into two bands. Okay, and with the help of these two set of filter, and then downsampling operation is there, then upsampling operation is there, then synthesis filter is there. So if you see, for example, spectrum of the signal is 0 to pi. So your one upper subband having spectrum from 0 to pi by 2 to this upper sideband, it is having from pi by 2 to plus pi. Okay, so in this case, if you want to design this structure, So you have to design these 4 filter is there. Means basic requirement for designing of this system is that we have to design these 4 filter. Okay. And in this case, there is no processing unit is there. For example, if processing unit is there, in that case, this is this one. So this 2-channel filter bank is also known as quadrature mirror filter bank, because one filter has mirror image of other one. So due to that, this 2-channel filter bank is also known as quadrature mirror filter bank. And if you go for in detailing and classification of filter bank, so if you see, there are 2 types of filter bank is there. One is 2-channel filter bank. If we divide our signal into 2 bands, and if we divide our signal into M bands, then it is known as M-channel filter bank. Okay. So for example, if we consider this structure, and in this case transfer function of this system, so in this case transfer function is T of Z, means that is T of Z is nothing but Y of Z divided by X of Z. And in this case, if it is just like a delay function, means that is Z raised to power minus K. So if you see time domain, same thing, and that transfer function time domain, that is Y of n equal to X of n minus 1. So in this case, your output is nothing but delayed version of your input signal. So that structure is known as perfect reconstruction filter bank. And if your output is not exact replica of input signal, in that case, it is known as nearly perfect reconstruction filter bank. So perfect reconstruction filter bank can be designed with orthogonal. It can be further classified in 2 types. One is orthogonal filter bank and another one is bi-orthogonal filter bank. And bi-orthogonal filter bank we can design with linear phase, non-linear phase. And if you see M-channel filter bank, in this case there are 2 types of filter is there. One is uniform filter bank, another one is if we divide our input signal into uniform band, then it is known as uniform filter bank. And if we divide our signal into non-uniform band, in that case it is known as non-uniform filter bank. Okay. And based on designing, we can classify this uniform filter bank as well as tree structure filter bank, parallel structure modulation based, and we can tree structure filter bank can also be classified. See, in this case, this is parallel structure. In this case, if you design this parallel structure, then this side, analysis filter is M and synthesis filter is also M. So you have to design 2M filter, and 2M filter you have to consider in such a way that whatever your design problem formulated for optimization, in that case you have to consider these all filters simultaneously. So in this case, designing cost is more. Okay. But if you consider tree structure approach, in tree structure filter bank, in this case, we are considering 2-channel as a basic building block. For example, in this case, we have divided into 2 bands, and then we are applying at lower subband as well as upper subband. Again, we are applying decomposition level. So in this case, there will be 4 channel. Okay. And again, if you apply this level, further decomposition level, so for example, this is first stage, this is second stage, and decomposition is stage is third one. So there will be 8 channel. And if decomposition level is fourth stage, there will be 16 channel. So we can say that, for example, number of stages we denote with M, then number of channel are equal to, number of channel is equal to 2 raised to power M. Okay. And in this case, bandwidth of each channel is same. So in this case, designing problem of this filter bank is we have to design this your filter bank structure. Okay, so your design problem, whatever is there, that is in terms of these 4 filter is there. Okay, and its parallel equivalent of this structure is we are driving parallel equivalent. In this case, we are considering noble identity of multi-rate signal processing. Okay, so in multi-rate signal processing, there are 6 noble identity, 3 for downsampling and 3 for upsampling. So in this case, we are considering a noble identity of downsampling. For example, for this structure, we are considering noble identity third, okay, for downsampling and upsampling, okay. And in this case, for example, we are saying that your most of the information is lying in lower frequency range, and higher side, we higher frequency range, we are saying that is nothing but noise. So in this case, we can neglect, we are not applying further decomposition, just like this. In this case, we have not applied further decomposition. So in this case, there are 3 channels, and each channel having non-uniform bandwidth, okay, and parallel equivalent of this structure is this one, okay. So we have discussed this basic structure of your multi-rate signal processing. Then how we can design these filter bank, okay. So in this case, what is designing problem of this filter bank, that we will discuss in terms of, if we discuss analysis of filter bank. For example, we are going to consider this filter bank structure, this 2-channel filter bank, how we can design with the help of linear optimization. So in this case, if you do the analysis part, okay, if you do the analysis part, in this case, analysis part of this 2-channel filter bank and driving input output relationship. So based on this, your input output relationship is this one, okay. In this case, first term is x of z and second term is x of minus z. So this your first term. In this case, your x of z means your input signal in z domain, okay. And this x of minus z, it means that is nothing but aliased version of your signal, okay. So for example, in this curly bracket, whatever is given, we can denote with t of z, and in this curly bracket, we can denote this is a of z. Then your input output relationship of the your system is this one, okay. And in this case, this t of that is distortion trans, we can name it as distortion transfer function, and this a of z, we can name it aliasing distortion transfer function. So if we consider input output is this one, in that case, your system, whatever your 2-channel filter bank is linear time varying system, okay. And if you remove aliasing distortion in 2-channel filter bank, in that case, your filter bank structure is nothing but linear time invariant system, means it will satisfy linearity property, time invariance property. So that resulted if you remove this one, okay. So for removing aliasing distortion, we are putting this term, this a of z equal means this term we can remove, put equal to a of z, means this x of minus z, that is not going to become 0. It is aliased version of your signal. We can assume this term to remove, make system time invariant system. Then we can put this a of z equal to 0. So if you put a of z equal to 0, then your condition reduced to this one, okay. So in this case, you see your synthesis filter is drive in terms of analysis filter. Earlier we have to design 4 filters, but in this case, if you consider aliasing cancellation condition, then designing problem reduce in terms of 2 analysis filter, okay, 2 analysis filter. So if if after putting aliasing distortion condition, then your input output relationship is this one. And if you calculate frequency response of your filter bank, for that we are evaluating this transfer function on unit circle. So in this case, your input output relationship is this one, okay. And in this case, for example, if we assume this t of z as a all pass transfer function, okay, then your input output relationship is this one, means your output is nothing but that is scaled version of your input signal. So in this case, your system is preserving only magnitude, okay. The phase, there is phase distortion. So in this case, whatever your structure is said to be magnitude preserving, okay. And if you consider your T of Z as a linear phase transfer function, means that is imparting linear phase, in that case that structure is known as phase preserving, but there is magnitude distortion is there. Okay, so as we can remove, as we have discussed in subband coding, there are in multi-rate signal processing or subband coding, there are three type of distortion is there. But that aliasing distortion we can remove if we consider that synthesis filter in terms of analysis filter. Okay, so next thing, that phase distortion if you want to remove, in that case your filter bank, that two analysis filter, that must be FIR filter. Okay, that must be FIR filter. Okay, and in this case we have already discussed that if transfer function of filter bank is just like delay function, so in this case your output is nothing but delayed version of your input signal. Okay, and this is this structure. Okay, this is perfect reconstruction filter bank, but in this case it is not providing good frequency selectivity. Okay, so if you want to remove phase distortion in subband coding, in that case you have to consider your H node Z structure to be type 1 FIR filter or type 2 FIR filter. Okay, and FIR filter means its impulse response of the symmetry condition, and in that case generalized frequency response is given by this mathematical expression. Okay, and this H node bar omega, that is nothing but amplitude response, or it is real function of omega. Okay, so if you calculate, if you put this term in your transfer function of filter bank, then condition is reduced to this one. Okay, and in this case if we consider n is equal to even, so in this case your frequency response of filter bank at quadrature frequency, that is going to become 0, so that is not required for perfect reconstruction. Okay, so we cannot consider type 1 FIR filter. Okay, we have to do type 2 FIR filter. In that case order of filter is odd. Okay, and so if we consider type 2 FIR filter, then frequency response of the filter bank is this one. Okay, so if you see within this curly bracket, if it is equal to 1, then we can say that your frequency response of filter is nothing but delay function. Okay, that is nothing but delay function. So whatever your output you are applying input signal, if there is no processing unit is there, in that case output is nothing but delayed version of your input signal. Okay, but if this condition is satisfied, then there is perfect reconstruction is there, and we can say that output is nothing but exact replica of input signal. If this condition is not satisfied, in that case there is amplitude distortion. Okay, so in filter bank structure, amplitude distortion, this condition is not going to satisfy, so there is amplitude distortion is there, and that amplitude distortion in two channel filter bank we can minimize with the help of optimization technique. Optimization technique, you can use linear search optimization technique, you can use gradient based optimization technique, you can use swarm based optimization technique. Okay, depending upon your problem formulation, you are making problem in time domain, you are making problem in frequency domain, and whether your problem is multimodal surface problem, whether number of variable is 1 or 2, depending upon that you can use suitable optimization technique. Okay, for example here, for example we are using linear optimization problem. Okay, linear optimization problem for design of two channel filter bank. Okay, so if you do the literature part of your filter bank, in that case we came to know that amplitude distortion we have minimized aliasing distortion completely, and phase distortion we can completely remove if you use prototype filter as low pass as a FIR filter. Then amplitude distortion is there, that is minimized with the help of optimization technique. Okay, so here if you do the literature part, then you will feel that you will find that amplitude distortion dependent upon cutoff frequency. Okay, so for example, if you take different value of cutoff frequency, in that case you will see that smaller value of cutoff frequency there is peaking effect, and if you take larger value of cutoff frequency, in that case this is this one. So here design problem is reduced to find out the suitable value of cutoff frequency, so that amplitude distortion at quadrature frequency is less. Okay, for example, if you see in green, in this case amplitude distortion is less at quadrature frequency. Okay, so designing problem of filter is nothing but that is reduced to find out the suitable value of cutoff frequency, so that amplitude distortion is less. Okay, and if you see analysis of two channel filter bank, then perfect reconstruction is possible if this condition is satisfied. Okay, and if we evaluate this condition at quadrature frequency, then this is reduced to this one. This is nothing but magnitude response of design filter at quadrature frequency. Okay, so here also if you consider this is ideal one, so here design problem is reduced to find out the suitable value of cutoff frequency such that their filter coefficient at this quadrature frequency is this one. Okay, so we have developed one iterative linear search optimization. In this case, whatever your variable is, that is your cutoff frequency. Okay, so in this case we specify the stop band attenuation, pass band ripple, and pass band as frequency. Means we are specifying the design specification that is required for design of your prototype filter. Okay, then we initialize the counter, step size, magnitude response of your prototype filter at quadrature frequency. Then we specify the tolerance. Okay, this approach is simple approach that is based on bisection approach. Well, the finding the roots of any polynomial based on the bisection approach. So same concept is used here. Okay, and then we are estimating the order of filter, cutoff frequency. Then we are designing your prototype filter using windowing technique before optimization start, and then calculate the magnitude response of design filter at quadrature frequency, and we are checking whether this magnitude response of prototype filter is comparable to your magnitude response in ideal condition. Means we are calculating some error with this mathematical formula, and if this deviation is this error is comparable to tolerance, in that case we are stop that, and whatever the filter coefficient is there, that is optimized one. Okay, that is optimized one, and we can use for designing your filter bank. And if this condition is not satisfied, in that case we are varying your cutoff frequency in two ways. Okay, for example, if your magnitude response design filter is less than in ideal condition, then we increase the cutoff frequency by step size. Otherwise, we decrease cutoff frequency by step size. Okay, and we redesign your prototype filter using new cutoff frequency, same order, and again we are calculating error, and we are repeating this process till iterative process till your condition is satisfied. Okay, so in each iteration, just like in bisection approach, we are reducing the step size. So same thing in this case also, in each iteration we are reducing the step size. Okay, by half. Okay, for example, we have taken this design specification, and in this case we have used same iterative technique for design of this one. In this case, this is your prototype filter bank response, and these are the error plot. Okay. Similarly, you can use different window function also, and you can estimate amplitude, distortion, peak reconstruction error, a number of iteration, and optimum cutoff frequency. Next thing, in this case, for example, if you want to design n-channel filter bank with the help of linear search. So in this case, as we have already told that cosine modulated filter bank, if you want to design this m-channel filter bank, in this case, we have to design single prototype filter, and rest of other we are driving from this one. So here, whatever coefficient we have to derive, that is your single prototype with the help of some optimization technique. So in this case, if you do the literature, how we make the problem here, if you do the literature survey, then you will feel that this is your ideal condition. Okay. And if you evaluate this condition at quadrature frequency, then problem is reduced, design problem is reduced to this condition. So here, design problem is reduced to estimate the suitable value of cutoff frequency, so that filter coefficient at this one is this one. Okay. So in this case also we have used optimization technique. Here the variable that to be optimized, that is cutoff frequency, single variable is there. Okay. So single variable is there. So we have used linear search. Okay. If multivariable to be optimized, in that case, we can use some other technique also. Okay. So for example, we have taken this specification. In this case, this is your filter bank response. This is your prototype filter response, and this is your filter bank response. Okay. This is, and in this case also we have taken different, and then we have calculated amplitude, distortion, aliasing distortion, and convergence, how much your optimization technique converts. For example, number of iteration required, this is this one. And in this case you will see that computational time required, that is also less. Okay. And we can use, for example, in some application also, for example, if you use this application is biomedical signal, so in this case you have to consider some specific property in optimization your design problem of your filter bank, so that that will give consider best performance in that area. Okay. So here we have designed this 8-channel filter bank, and we have considered some spectral property of your this, and we have designed, and that filter we have again consider for subband coding or in 8-channel and reconstructed. So this is original one and this is reconstructed one. In that case, there is no difference between the reconstruction error is less. Okay. Similarly, if we have used again that iterative technique for design of another cosine modulated filter bank, that is weighted least square technique is used in this case also. So in this case, we have considered two things, mean channel overlapping as well as channel overlapping we have considered. And in this case, your iterative technique is based on weighted constraint least square technique and based on same perfect reconstruction error. So whatever the proposed technique for this one, that proceed with following step. First, we specify the design specification. So in this case, your design specification is nothing but we are specifying roll-off factor, passband ripple and stop band ripple, and this is error ratio. And then we are initializing the counter, step size, magnitude response of your prototype filter in ideal condition, and also specify the tolerance. And then we are considering these some parameter is there, del p, del s, and in this case we are calculating cutoff frequency with the help of this one, and then we are calculating this pass band edge stop band edge frequency with the help of roll-off factor. And in this case we are assuming pass band edge frequency is slightly less than this one. Okay, so here in this case also we have to optimize your cutoff frequency. Okay, so in this case also your design problem is reduced to find out the suitable value of cutoff frequency so that your perfect reconstruction is achieved. So here also single variable is there that to be optimized. Okay, so we are designing your prototype filter with whatever design specification is there, and same thing in this case we are calculating magnitude response of design filter at this one and also error. Okay, and same thing in this case, just like if magnitude response of design filter is less than your ideal one, in that case we are increasing the cutoff frequency, and same we are going to decrease with the help of step size. Okay, and in this case again we are computing omega p omega s with this relation, and we redesign your prototype filter using new omega p omega s and same order. Okay, and we are going to calculate the error, and we are repeating same iterative techniques. Okay, we are repeating same iterative techniques and till tolerance is satisfied. If tolerance is satisfied, then we can say that whatever filter coefficient we are getting, that is optimized one, and whatever your cutoff frequency is there, that is also optimized one. Okay, so for example, we have designed 32 channel cosine modulated filter bank with this specification. Okay, in this case this is your prototype filter and this is your filter bank response. So okay, and we have also used this 32 channel filter bank for subband coding of ECG signal. In this case we have divided this ECG signal in 32 channels, and then again we have reconstructed, so you will see that there is no error. Okay, so in this case also we have optimized for designing of this M channel filter bank with linear search optimization. In this case we have also optimized one single cutoff frequency. Okay, second thing, if you want to design, okay, for example your practical signal, if you see the spectrum of your practical signal is not uniform, for example if you consider EEG. Okay, so in this case whatever we have used linear search optimization for design of non-uniform filter band for EEG application. For example, in EEG, the spectrum of EEG signal is something 5 bands are there. Okay, and band have non-uniform bandwidth. Okay, so in this case, we have considered, for example, as we have already discussed, tree structure filter bank. This is tree structure uniform filter bank, and in this case, this is non-uniform tree structure filter bank. In this case, we are not applying further level of decomposition on this one. Okay. For example, if you consider this structure, and in this case, parallel equivalent of this structure is this one. Okay. In this case, we are denoting this H naught equal to this one, H1 equal to this one, H2 equal to this one. Okay. And if you see the relation for 3 channel filter bank, relation is this one, and similarly if we consider M channel filter bank, okay, 4 channel filter bank, then structure is like this one. Okay, in this case your relation is like this one. Okay, so in this case, if you consider this structure, for example, okay, this structure, in this case if you formulate the design problem, so just like formulating the design problem, if you see this condition is satisfied in ideal condition. Okay, and for example if we consider 3 channel filter bank, then condition for 3 channel filter bank is this one. Okay, and in this case if this we are putting this relation in this equation, then condition is this one. Okay, and here concept is that if we have that upsampling operation is nothing but there is L minus 1 consecutive 0 is introduced. Okay, so if you calculate energy of your original signal and upsample signal, in that case energy is same. So same concept is used here. Okay, so if you use same concept, then this is equivalent to this one. Okay, and similarly this is equivalent to this one. Okay, and in this case, if you calculate, if we further simplify this equation, if you further simplify this equation, then this is this one. Okay, this is this one. And in frequency domain means we, if Z domain is there and if we evaluate on unit circle, then we can put Z equal to e raised to power j omega. Then this relation is 10 to this one. Okay, and if you calculate this condition at quadrature frequency, okay, quadrature frequency, then your design problem is quadrature frequency, this is this one. And if you assume this is equal to x, then this is fourth order polynomial. Okay, this is fourth order polynomial, and this fourth order polynomial based on factorization approach, we are finding the roots of this polynomial. Okay, and in this case again, this is one root is this one and another root is this one. This is imaginary root, so that is not possible for practical system. Okay, so your problem is reduced to this one. So here your design problem is reduced to this one, means you have designed your filter in such a way that magnitude response of your prototype filter in ideal condition is this one. Okay, this is new PR condition. So same this new PR condition we have in this case, whatever you are we are optimizing your cutoff frequency so that this condition is achieved. Okay, so here also your design problem is reduced to estimate the optimized value of coefficient so that at quadrature frequency is this one. So for solving this problem, we are optimizing here the your cutoff frequency. Okay, so we, whatever your iterative approach is this one, in this case we are specifying your design specification, counter, magnitude response of your prototype filter at this one, and also some tolerance. Then order of filter we are estimating with this relation, cutoff frequency with this relation, and then we are designing your prototype filter with whatever cutoff frequency you are getting. And we are using window functions, different window function we are using, and then we are calculating magnitude response of design filter at quadrature frequency, and also calculate the error before optimization. Okay, and then we are checking whether this error is comparable to tolerance. If not, then we are varying the cutoff frequency in two way. We are checking that whether magnitude response of design filter is less than ideal condition, then we are increasing the cutoff frequency by step size, otherwise we decrease. Okay, and then we redesign your prototype filter using new cutoff frequency, same order, and also calculate the magnitude response of your filter, and this process is repeated till tolerance is satisfied. Okay, so here single variable is there that to be optimized and some condition is there. Okay, so in all three example, in two channel filter bank and in n channel filter bank, and as well in non-uniform filter bank, first we have make the design problem, we are formulating the design problem, and then we will think what is the ideal condition is there, and then we will check that ideal condition is depending on what variable. Okay, so here in all three cases we are calculating the filter coefficient, and that filter coefficient is dependent upon the cutoff frequency. Okay, so that cutoff frequency we are optimizing that cutoff frequency with the help of linear search. And in this case, some perfect recursion condition, some condition is considered for stopping that criteria. Okay, so in this case, we have taken this design specification and we have designed these 3-channel filter bank. Similarly, this is 4-channel filter bank, and similarly, this is 5-channel filter bank we have designed. Okay, and in this case, so and we have in all 3 examples, in this case, depending upon your problem formulation. Okay, for example, the same problem you can solve with the help of swarm optimization also. Okay, swarm optimization also, and same problem you can solve also with gradient based search also. But in this case, we have considered linear search because it will converge in less number of iteration and computational time is also less. Okay, and so that we can use for real time application. But in swarm based techniques, if you use for solving this problem, in that case, number of iteration is more. Okay, and in each iteration, in each run, you will get the different solution. But in this case, either you run many times, you will get the same solution. Okay, so this is all about today's lecture. Thank you. Okay, if you have any query, we can discuss.
Participants, you can put up your questions in the chat box.
And you can also mail these queries to us. We'll share with the sir.
You can type.
You can directly mail to me also.
You can write in the chat box also.
And any student interested to work in this area for PhD, he is most welcome. Gate qualified.
Thank you, sir, for giving the participants an opportunity. Throughout the country, many faculty members and participants are attending this program. More than 470 students have registered for this program. PhD scholar as well as faculty member.
Okay.
Thank you so much, sir, to be here and to give this presentation to us.
Participants,
thank you for
if you
inviting
have,
me.
any query, please write in the chat box. Sir, please be there for 2-3 minutes. We are
Okay, I am
at the chat box regarding the queries.
Sir, there is a one query. Can you suggest any book to refer for this?
You can use multi-rate system and multi-rate signal processing by PP Vaidyanathan. PP Vaidyanathan and multi-rate signal processing by E. Kocher.
Okay, sir.
Okay. And another book is also there, that is multi-rate signal processing for communication, that is Professor Harish.
Okay, sir.
Okay, that book are costly.
Sir.
And you can also recommend that is SK Mitra book also for this one, digital signal processing for by SK Mitra.
Thank you, sir, for joining our program and enlightening all the participants.
Thank you.
Thank you, sir.
May I leave?
Yes, sir. Yes.
Thank you, sir. Thank you
Thank
so
you.
much.
Sure.